A second part of chapter 7 questions, and this is number 6. Ice has a specific heat of 0.50. How much heat must be added to raise the temperature of 1 pound of ice from 50 degrees to 30 degrees? Well, first, 50 to 30 degrees, you know, that's a 30-degree change, right? From 80 degrees, and you're raising it from 50 to 80, you got 30 degrees. So that's what we're going to be working with here. So we know how much we want to raise it. We want to raise it 30 degrees. Now it talks about specific heat. Specific heat is how much heat energy is needed to raise 1 pound of any substance, any material, by 1 degree. For instance, 1 pound of ice, 1 pound of water by 1 degree. Now, does it? Let's take water here. I think that's what it's asking for. Ice. Okay, ice has a specific heat of 0.50, which means it takes 0.50 to heat to raise 0.50 BTUs is what it's talking about. So half a BTU to raise 1 pound of ice by 1 degree. Now, for water, it takes 1 BTU to raise it 1 pound by 1 degree. That's a specific heat. Water has a specific heat of 1 BTU. Ice has a specific heat of half a BTU. Air has a specific heat of 0.24 BTU. So you can raise the temperature in air faster than you can raise, or with less energy than you can with water. For instance, water, it takes 1 BTU to raise it 1 degree. So say we're going to raise it 5 degrees, it takes 5 BTUs to get water to go up 5 degrees, heating it up or whatever. But with air, it takes almost a quarter BTU. So if we're going to raise it 5 degrees, we multiply the specific heat, that's a formula, specific heat times the degree change, is 5 degrees. And so we get, let me see, easier doing it this way. It's 20 times 10, okay, that's 2.2. So it takes 2.20 BTUs to raise air temperature by 5 degrees. When water it took 5 BTUs. So it takes less energy to heat up air than it does to heat up water. Again, the formula is very simple for this. Take the specific heat of whatever substance, but we're going to call that A, specific heat, and then we'll say the degree change, that's how much you're going to change it from 1 degree, 5 degrees, whatever. We'll call that D, okay? And then you'll find out how many BTUs, the total energy. So total energy, or heat, we'll say total heat. Heat is, we'll say H. So the formula is A times B equals H, or specific heat times the degree change equals total heat. So let's just fill in the numbers here, right? If I have, I'm changing, let's say brass. Brass has a specific heat of 0.09, okay? And I want to raise it by 20 degrees, okay? Plus 20 degrees. I want to know what the total heat I need is. So we take the specific heat for brass is 0.09. So here on A, we're going to fill in, so it's A times D equals H. So we're just going to fill in the numbers. A is 0.9, so we'll put 0.9 for A, and multiply times the degree change, 20, okay, and then we get the total heat, which is, so 20 times 0.9, I'll just do that real quick. It's 18, 0, 0, 180, 2, okay, so it's 1.80 or 1.8. So you have 1.8 BTUs is needed to raise brass by 20 degrees. 1 pound of brass. Okay. So the answer for 6 is C, 15 BTUs, because the question was how much specific heat is needed to raise 1 pound of ice by 30 degrees. So ice is 0.5, that's specific heat. 30 degrees is a change. So 30 times half, that's 15. That's your specific heat, 15 BTUs. Okay, number 7. When heat is carried from one object to another by means of liquid or gas, this is transferred by, that's convection. I'm sure we know that. Rather than explain it to you, I'll show it to you in the book. It was, and see if I remember what page that was. Yeah, there you go. Do I have that part? Okay. Remember the 3 forms of heat transfer? Doesn't really show you a good picture here, but it's in page 7.7. You got conduction, which is where you're actually touching something here, the flame's touching the pipe. You got convection, which is transferred either by air or it could be by fluid. So in your refrigeration cycle, you are transferring heat by what? By the refrigeration of the fluid. So that's how we're transferring heat. So it will be a convection cycle. And radiation, of course, you got heat waves. So that one is A, convection. Number 8, traps at the bottom of the suction line risers help to, this is in your book, it's create turbulence, which helps entrain oil and carry it to the top of the riser. That's, I'm going to be honest, I don't know too much about that. I'll show you a picture here. This is what it's talking about. It's right here, the little traps. This is page 747 and 748. And here it shows the little traps here on the bottom. If you can see it right here. Over on this side. I'm looking backwards, so. And then here on this side too. You got little traps here. So it causes turbulence and helps get the oil to the top. So that will be C. Number 9. In a closed container, a gas exerts an equal pressure in all directions. Well, it's simple to understand. We can have a picture here. If you have, say, a can, any kind of can, doesn't matter, and you have gas in there, say air, compressed air. Well, air is going to fit the canister which it's in, so you're going to have pressure on all sides equally. Well, if you had a glass of water, water is only going to exert pressure on the side and down. Water doesn't shoot up and put pressure. Gas does. It goes to all sides, and that's what it's talking about there. In a closed container, this is closed, a gas exerts an equal pressure on all directions. And that one, I believe it's, if you want to read more on that, that's page 7.8. This right here, see? Shows water is sides and down. Gas, so here's a solid, just down. That's right. You got weight, and here gas, all directions. Okay. Number 10. When a pressure gauge reads 60 psig, there is an absolute pressure of. This one, okay, you have two. On a barometric pressure, you have, or barometric scale, you have 2 different kinds of calculating pressure. You have absolute pressure, just here, and then you have gauge pressure, right? A gauge pressure is just a little different. Gauge pressure here, 0 for gauge pressure, is actually the same as 14.7 in the absolute scale. So 0 on the absolute scale would actually be a vacuum in the gauge pressure. That's why it says PSIG, pounds per square inch on the gauge. It's not the same. So whatever your gauge pressure is, just use G for gauge pressure. You add 14.7 to get the absolute pressure. Okay, so if my gauge pressure is 60, just insert it there for there. You add 14.7, so you have an absolute pressure of 74.7. Now remember, PSIG is gauge pressure. PSIA is absolute pressure. Here it's asking for the absolute pressure. So you got 60 plus 14.7. This is your gauge pressure. This is the, remember we added, that's the formula. So you have an absolute pressure of 74.7. So the answer is 74.7 PSIA for absolute pressure. And that is D. Okay.